And at the time, you kind of joked about it, but that was the genuine reaction I got. People were like calling me the moon guy, and they were like, "What's this idiot up to? Like, he's talking about looking for exo-moons."
Never changed, did it? It just never changed. It just went on after Cambridge.
It was the same reaction. Same reaction as that.
Exo-moons with Kepler, so heck.
Yeah.
Why moons? Now, I can think of this from the funding perspective. They're like, we've just found these planets, and now you want to go a level down and go moons? You know, what are you going to do next? You're looking for individual cars and stuff on these planets. Why are we interested in moons? Why do we want to see moons? What's the deal with this?
Yeah, I normally say there's like three main reasons that are kind of the nice, tidy reasons to put into proposals to talk about with this and to communicate to the public. And then I could also briefly mention how I personally got into it, because I didn't really think of it that way when I first started doing it. So the three sciencey reasons to do this. One is that these moons may very well be habitable planets in their own right, or habitable worlds, I should say, in their own right. We're in this obsessive game of trying to figure out if we're alone in the universe, what the frequency of Earth-like planets is, and really Earth-like moons should be a component of that if we're going to do this job properly.
So it's more real estate for life.
Yeah, and it's particularly important because M dwarfs have this tidal locking problem. The habitable zone is very close to M dwarfs. That is the most abundant star in the universe, but planets in the habitable zone there would have one side of their planet always facing the star all the time. It's probably not great for the climate, but the moon would not experience that. Even if the moon is tidally locked to the planet, it would get equal amounts of illumination. So actually, moons could be really interesting places for life to start and thrive around those M dwarfs. The other reason is that when we look at this, that's kind of intrinsic habitability. And then I sometimes make up this phrase extrinsic habitability. And that's thinking about the influence the moon has had on the Earth. So it's been thought that, at least hypothesized, I would say, that the moon has had an important role on the evolution of biology on this planet. It may have even been responsible in some indirectly for kickstarting life on this planet. You had this giant impact event that happened, 4.5 billion years ago. And that may have stripped off a lot of the thick, heavy crust that was sat on top of the Earth. And then you just have a thin crust on top, which is much more amenable for plate tectonics, which enables a carbon cycle on those planets to happen. The moon also raises very large tides on the Earth, of course. It was much, much closer to us 4 billion years ago after it just formed than it is now. It's actually receding away at 4 centimeters per year. So if you rewind the clock back, those tides would have been so big that they would have, the 2 tides a day, they would have covered like half a continent. Wow. So you would have had just rock pools all over the place, which is kind of exactly what you want for starting life. You want concentrated pools of liquid and organic molecules in a single area. So it's been hypothesized that the moon could be good for that. And finally, it also stabilizes the obliquity of the Earth. If we took away the moon, the axial tilt of the Earth would just sort of drift around. That's actually what happens for Mars. It just wanders around without a big moon. So these reasons have been cited as, having a big moon. If you find Earth 2.0, one of the first questions you might ask is, does it have a moon 2.0? Because that seems to have had an impact here on Earth. And then finally is just to understand how moons and planets form more generally. The moon, as we just mentioned, it has this very strange origin. It's this giant impact. We have moons like Triton around Neptune. They go around backwards in a retrograde orbit. And then you have the moons of Jupiter, which seem to have formed from leftover material. So you have, that seems to be a reasonable way to make moons, but then you have these 2 freaks of the solar system, and it's not obvious if they're freaks. Maybe the Earth-Moon system is an inevitable outcome of planet formation, and all planetary systems have them, and we're not unusual to have one. Or maybe we'll do all this exo-moon surveying, and we'll find out that the Earth-Moon system is like a real gem. Like there's just nothing like it anywhere in the universe, and that would be really interesting. If we find out there's nothing else like the Earth-Moon system anywhere else in the universe, then I would maybe lean a bit more towards that influence of the moon on the Earth and its early history.
You'll set off the religious nutters as well, of course, if you find that the solar system is unique in the entire universe.
Yeah, I try to avoid, no matter what you do, people will always be able to imprint their beliefs on your phone.
They're always going to throw their confirmation bias onto it.
Yeah, exactly. I try not to get too hung up on that. So that's the science reason. The personal reason, to come back to it, was really just the novelty of it, I would say, and the fact no one else was doing it. So
that's always a good reason.
Yeah, no one else was doing it. I'm going to do it. And I wrote my first paper on that. Had the idea pretty early on in my PhD that this could be an interesting avenue to explore. And at the time, you kind of joked about it, but that was the genuine reaction I got. People were like calling me the moon guy, and they were like, "What's this idiot up to? Like, he's talking about looking for exo-moons."
Never changed, did it? It just never changed. It just went on after Cambridge.
It was the same reaction as that. So I guess I was used to it. Maybe that's why I didn't care. I was like, that's just I always get that reaction.
Yeah, just own it.
Yeah, and people were like, "Come on, you've just started finding hot Jupiters, for God's sake. And now you're going to try and find Earth-sized exo-moons? Like, come on, get a grip." And it was really seen as fringe for a long time. And I have to say, over time, even though we really don't have any like super convincing detections yet, we have some interesting candidates.
Well, I want to know about Kepler 1625b in a second. So
yeah, we can talk about that candidate. But I guess even regardless of that, the field has gained legitimacy, I think, over time. There's a lot of people writing papers about exo-moons now. And I got a job, as a professor, pretty much because of my track record on exo-moons, I think. So you can make a career, but I remember very early on being pushed to not do it. I remember people saying to me, "You should seriously consider stopping this exo-moon shit and just do the safe stuff. Just do hot Jupiter work.
That's not fun.
That's way safer." No. I was like, I don't want to do that.
No. You did the right thing. So how do we, if it's transits to find these planets, how do we get the moons is it second order effects on a transit of a planet? How do we go about finding these moons?
Pretty much second order is where that's all the fun is at in the second order, as you'd say in a physics class. So we tend to look for two effects. One is that the gravity of the moon on the planet. So if the Earth moon system, you tend to think the moon goes around the Earth, but that's not quite true. The Earth and the moon go around a common center of mass. And that center of mass actually lies about 1,000 kilometers beneath your feet when the moon's overhead. So it's inside the Earth, but it's actually quite close to the surface. If it was outside the Earth, you might call that a binary planet, actually. That's one proposed definition. So that means that the Earth is orbiting around that center of mass point, and thus it's kind of gyrating around. And that means that every time it whips around on its orbit and causes a transit, sometimes, depending on the phase of the moon, it will come in early and sometimes it will come in late. For the Earth-Moon system, it's about 5 minutes. So an alien looking at the Earth-Moon system transit, they'd notice the Earth sometimes transits 5 minutes early, 5 minutes late. So they'd know for sure the moon was there. The other method you might use is just to look for the actual eclipse of the moon itself. So if the planet's passing in front of the star, depends on the orientation, but there's a good chance the moon will pass in front of the star as well. So you'll get a second dip either before or afterwards.
And this looks like what you saw with the candidate you were looking at, the Kepler 1625b for that, where you got this secondary dip potentially from a moon going around an exoplanet. Is there any follow up on that, or is that still a candidate that potentially we could get more information about at a later date?
I'd call it still a candidate. There's a very long story about that. Honestly, we could talk for hours about that damn candidate, and I don't want to bore everyone about it. But we saw in Kepler data something weird about this planet. It was a Jupiter-sized planet orbiting a fairly solar mass star, and it was nice and wide it was on a nice wide orbit. It's exactly what we want for exomoons. We don't want planets too close to the star for exomoons. And it was the right size. We think Jupiter-sized planets are best. So we saw these interesting qualities about the planet, and the fact that it had these extra kind of wiggles in the data made us think, hey, let's ask for some Hubble time to try and follow this thing up. So we got the Hubble time, and we saw this great big fat transit occurring after the main transit. And in the previous paper, we'd hypothesized it was a Neptune-sized moon, and actually the dip that we saw corresponded to exactly a Neptune-sized moon. So at that point, it was pretty exciting. I was intrigued, but I was trying to keep everything in check. Then we looked at the fits a bit more carefully, and we noticed that the planet was also, it transited too early. It transited 78 minutes earlier than it should have done. So there was a big TTV in this system, a transit timing variation in the system as well. And
not
the direction,
not Twitch TV then, not you on Fortnite.
transit time.
Dave Kipping TTV.
Yeah, maybe we should have a TTV channel.
You should have.
On Twitch.
That'd be good.
Yeah,
we'll talk about that offline.
Okay, and the TTV was exactly in the right direction for where the moon appeared in the data. So it's actually the planet appeared to come in early, and the moon appeared to come in late. So the kind of the central mass was in between them. So it's exactly what you'd expect. So we got pretty excited, but at the end of the day, we only really had this one strong piece of evidence, which was the Hubble data.
Yeah.
And you want to see it multiple times.
Yeah.
In one sense, maybe we shouldn't have published it. Maybe we should have waited for more data and just waited and wait. But it was a 300-day period planet, and our proprietary period on the data was 6 months.
Yeah.
So after 6 months, everybody gets the data, and everybody knew what we were doing because one of my colleagues had accidentally tweeted it out, which didn't help at all. And we had all these journalists just fishing around it for months.
Yeah.
So I knew it was hot, and I knew if we had to do something with it. So we published it as a candidate, and we tried to be very careful with the language of that.
You've got to put your flag on it while you can, haven't you? You've got to...
Yeah, we'd say, look, we don't want to not say anything about this, because otherwise that looks suspicious if you just be quiet about it. But here it is.
The government's been round. We don't want you to say anything about all the aliens that are coming up.
Yeah.
At first, it's all beautiful, and soon you're an Aztec base, catnapping all the local tribes and killing whoever's the tallest or the smartest.
The big conspiracy tinfoil hat stuff.
Yeah, exactly.
So we got it out there, and then since then, 2 teams have had a look at it independently of us. One team finds the same dip as us, which is really reassuring. They are a little bit skeptical about the TTVs. They think maybe the TTVs could be caused by another planet in the system, in particular hot Jupiter in the system. I think that's very unlikely personally, and actually we'll have some data soon that we think would basically demonstrate that doesn't work.
Do you not see a similar dip in transits from other stars, or is this a very unique signature that you've seen with?
It's pretty unique. Yeah, this is pretty special. We don't see many of these things. And then there was a third team which had a look at it recently, and they think they don't see this moon-like dip, which they do see the TTV, but they think the moon-like dip is kind of fishy. They think it may be an artifact of the instrumental detrending or something.
Yeah.
So we actually very carefully looked at their data. They looked at our data. We've interacted with them a lot. They have no idea where we could have gone wrong. We have no idea where they could have gone wrong, and we're basically just kind of stuck at this point.
If it was to do with something in the hardware or the software, you'd think that they would show up on more transits, regardless of whether they have a planet or not, wouldn't you? I assume you did that check. It's like the thing to do.
Oh, we have 100-page supplementary material. Every check under the sun on this damn thing. I mean, essentially what we're pretty convinced of is that we have to correct for instrumental noise. Instrumental noise is a biggie to deal with. And we apply this correction, and when you look at what's left over, the data is what we'd call Gaussian afterwards, which means essentially it behaves like white noise. There's no wiggles. It's very clean and flat, which is what you want. Apart from in this one very localized region, which is exactly where the moon would need to be to explain the TTV, and there you see a moon-like dip occur. So that's why I tend to think that it's pretty suspicious that it's instrumental noise, because it's localized to this one specific packet that is exactly where the moon needs to be to explain the TTV. So I'm trying to, I have I can't say I'm completely unbiased about this, because I have a card in, what do you call it, a towel in the ring or whatever.
Skin in the game.
Skin in the game. That's the phrase I'm looking for. So I have skin in the game. So I don't want to say 100% I'm right. We need more data to really figure out the true answer. Unfortunately, we probably won't get it. So Hubble, we actually asked for time last time for Hubble, but it was before our press release came out and the paper came out. So I think that the reviewing committee just didn't realize it was a big deal at all. And then by then it was too late. We didn't get the time. And in transits every year, we have to wait 300 days for the next transit.
Sure.
And Hubble was on its last legs. It's unclear if Hubble will last that much longer. And we're kind of dubious that we would have the ability in the next transit to even detect this thing again. So it's really frustrating, but it might sort of sit there as a ambiguous case for a long time.